Hello, welcome to Thermal Physics. Today's lesson is just going to teach you a little bit about internal energy and what that means, okay? And in context of this spec, it looks like this. Take a pause, take a look, and you can read about that later. So let's get back to the beginnings of energy. What is energy measured in? It's measured in joules. You know that. I'm not going to go through these. Temperature is degrees C. That's what we've been taught to date. Why are energy and temperature the same? I will tell you that in a moment, but you might know that from GCSE. We'll see. Okay, we tend to think of particles as being the constituents of matter, and in a solid here, we can see in the diagram that the particles are bonded together, but they are moving, so they have a certain amount of kinetic energy. And because they are bonded, they have potential energy. We add those two things together, and we call that the internal energy of a substance. Temperature and heat, very important we understand the difference. Temperature is a measure of hotness. Two examples there, they're both at the same temperature. If you stick your fingers in each one of them, they will feel just as hot because temperature is actually measuring or is a measure of the kinetic energy of the particles. So the kinetic energy of the particles in the bath and the water in the cup are both similar, okay, same temperature. But heat energy, think about it. If you want to heat up that bath of water to 40 degrees, you need to heat it for longer than that cup of water. So heat is energy measured in joules, temperature is hotness measured in degrees C or something called Kelvin. They are not the same thing, but they are linked. Something called thermal equilibrium, one of the most important laws of thermodynamics, basically states this. If we have two objects next to each other, the hot object A is at 50 and the cool object B is at 10, the heat will flow from A to B until both objects are the same temperature. Very important, this gives a direction of time because heat always travels from hot places to cold places. And when they are the same temperature, we say they are in thermal equilibrium. And there is no net flow of heat either way. They're just sort of in equilibrium. Nice little diagram here. Once again, an idea from key stage 3, key stage 4. If we look at the particles in box number 1, this is a gas. Let's go back. It's in a gas. It's a cool gas because the particles aren't moving very fast. And you notice that they would have a low pressure in that box because they're not impinging on the surface with great energy. Look at number 3, particles have more kinetic energy, so therefore there's going to be more pressure in that box and they're at a higher temperature. Okay? Now this is important because it helps us to think about something called a thermodynamic scale. Thermodynamic scales start at 0 Kelvin, and essentially we call that absolute zero, which is the temperature at which a substance will have no internal energy. So if we cool down that gas to absolute 0, the particles are motionless and there is 0 energy there. We call that absolute 0. And in the case of the gas, it would have 0 pressure, 0 temperature. And to convert between Kelvin and degrees C is fairly straightforward. There you can read that in the box. And an important point to note is that a 1 Kelvin increase is equivalent to a 1 degree C increase. Okay, so the scales are both the same scales. It's just an offset to turn it into Kelvin. So absolute 0. Now, how do we find absolute 0? We get a box of gas. We measure the pressure and the temperature at a known temperature. So, for example, I don't know, water, which we call 0 degrees C. So here we go. P1 and T1 are the pressure and temperature of that gas at 0 degrees C. Okay? And if you notice, due to the theory behind this, and this is all linked to theory, not linked to a particular material, but in theory, any gas, if we cool it down, the pressure and temperature will eventually go to 0. So if we know one point along that graph, we can actually extrapolate and come up with a line for that graph. And as you see here, look, I've just put 3 points on there, 1, 2s and 3s, and the ratio of the pressure to temperature in each case are equal because it's a straight line. And that's how we find absolute 0. That's an experiment we can do when we all see each other again. Pause this, have a read. I'm not going to talk this through, but they show two gases in this slide. I was going to get you to do this, but I think it's rather trivial. If you want to pause the video, you can, and have a look where it comes from. But these are just examples of converting between Celsius and Kelvin. Oh, sorry, I was interrupted there. Here we go. So that's a trivial example there. Have a think about it. It's just converting between the two. Just be aware of that. So let's move on. Here are some questions. Do some reading around this first, and then see if you can answer these questions. Pause your video, back with the answers in 5. Okay, so questions 1 to 3, I've given some answers there. If you're really stuck or you don't understand where they come from, email me. But I am going to go through question number 4, part B. So it's question 4, part B. It's all about gas thermometers. So let's get some video up. Here we go. Ooh, good. Right, here we go. So we have a gas thermometer is used to calibrate a thermometer, and the pressure is given and the temperature is given. Okay, so first of all, let's refresh our brains here. So for a gas thermometer, we have a graph like this. If this was pressure and this is time, this is absolute 0 Kelvin. And here we go. The first bit of information we're given, we are told that when the pressure, and we'll call that pressure 1, when pressure 1 is 100 kilopascals, the temperature is given as 273 Kelvin. Okay. And it goes on to question 1. It says calculate the temperature when the gas pressure is 120 kilopascals. Okay. So let's call that P2. And P2 is 120 kilopascals, and they're asking us to find that temperature because we don't know it. Okay. Very, very simple. The relationship is this: P1 over P2. Ignore that. P1 over T1 is equal to P2 over T2. Now we want to find T2, so let's make T2 the subject of this equation. So let's do some rearranging, and we get T2 is equal to P2 over P1 multiplied by T1, and then we can actually calculate that. Here we go. What's P2? P2 120 kilopascals divided by 100 kilopascals multiplied by 273. The kilopascals cancel, so it's equal to 1.2 times by 273, which equals, let's get Mr. Calculator out. Equals 327.6. Let's call it 328 Kelvin. Okay, very important. It's in Kelvin. Kelvin. Easy peasy. Okay, second question says calculate the pressure. So we're looking for pressure. We'll call that P2 again. We'll call that P2. When the temperature is 100 degrees C. Don't fall into the trap. We cannot use 100 degrees C. We have to convert that to Kelvin, and that turns out to be 373 Kelvin. Oh, somebody's emailing me. And that's 373 Kelvin. So let's do the sums again. Let's just, so we know that P1 over T1 is equal to P2 over T2. We are this time trying to find the pressure, so let's rearrange this again. So P2 is equal to, okay, let's bung the numbers in. We know that P1 is 100 kilopascals, 100 times 10 to 3 pascals, divided by temperature 1, which was 173 degrees. Let's move that up a bit. Sorry, 273 Kelvin, not degrees. Let's multiply that out by our temperature of 373. Okay, let's do the sums this time. Picked up my phone, the calculator. So we have 100 to power of 3 times by 373 divided by, whoops, let's get rid of that divided by, let's just delete that for a second. That equals that, and then let's divide that by 273, which equals, get a big number here, 136630.0366. Okay, now let's be realistic here. Look, this is all sort of beer mat physics, as I used to call it, sort of just back of the envelope calculations. I'm going to ignore all this rubbish here, and I'm going to sort of round this to something sensible. Let's call it 137,000 pascals or 137 kilopascals. Okay, hope that helps. Let's just double check those answers. We can go back using the magic. Let's go back. There you go. So 328 for the first answer, which is what we got, and we got 137 kilopascals. So enjoy, do some reading around the subject. There's a lot to get your head around with thermodynamics, and hyperphysics is a very good place to go on the internet. So bye for now.